When electrical voltage increases while the amperage remains constant, the power demand also increases proportionally. This relationship is defined by the formula power equals voltage times current, where power is measured in watts, voltage in volts, and current in amps. In a situation where the voltage is raised from 120 volts to 277 volts while maintaining a consistent current of 20 amps, the power increases substantially. Calculating this, 277 volts multiplied by 20 amps equals 5,540 watts. A number 12 copper conductor, rated for 20 amps at 120 volts, which equates to 2400 watts, is inadequate for handling the increased power demand of 5,540 watts. To accommodate this high power level at 277 volts and 20 amps, it is necessary to use a larger conductor. A suitable alternative is a number 8 copper conductor, which is typically rated for 40 amps or 8,800 watts at 277 volts, thereby providing a sufficient safety margin. Selecting the appropriate conductor size is essential for electrical safety and to prevent overheating and potential fire hazards. The National Electrical Code or NEC provides guidelines and tables for determining the appropriate conductor size based on amperage, voltage, and application. Always consult the NEC or a qualified electrician to ensure compliance with local electrical codes and regulations. Factors such as ambient temperature, conductor insulation type, and the number of conductors bundled together can also influence the ampacity or current carrying capacity of a conductor. Firstly, consider the ambient temperature. Higher ambient temperatures can reduce the ampacity of a conductor as the conductor's heat dissipation capability is diminished. Secondly, the conductor insulation type plays a crucial role. Different insulation materials have varying temperature ratings which affect the maximum allowable current the conductor can safely carry. Thirdly, the number of conductors bundled together in a conduit or cable assembly also impacts ampacity. When multiple conductors are bundled, they generate more heat, and the heat dissipation becomes less efficient, requiring dilating of the conductor's ampacity. It is imperative to consult the appropriate NEC tables and dilating factors to account for these conditions and select the correct conductor size for the specific application. Failure to do so can lead to overheating, insulation breakdown, and potential electrical hazards. In practical applications, when upgrading a circuit from 120 volts to 277 volts, it is not only the conductor size that needs to be considered, but also the associated electrical components. This includes circuit breakers, receptacles, and other devices connected to the circuit. These components must be rated for the higher voltage to ensure safe and reliable operation. For instance, a circuit breaker designed for 120 volts may not be suitable for 277 volts and could fail or create a hazardous condition if used improperly. Similarly, receptacles and other electrical outlets must be rated for the appropriate voltage to prevent arcing, overheating, and potential fire hazards. It is crucial to verify the voltage rating of all electrical components and replace them with components that are specifically designed for 277 volts. Moreover, when working with higher voltages, it is essential to follow strict safety protocols and use appropriate personal protective equipment or PPE. This includes wearing insulated gloves, safety glasses, and other protective gear to minimize the risk of electrical shock and burns. Always de-energize the circuit before performing any electrical work and use a reliable voltage tester to verify that the circuit is indeed dead. If you are not comfortable working with electricity or are unsure about any aspect of the installation, it is best to consult a qualified electrician. They have the knowledge, experience, and tools to perform the work safely and ensure compliance with all applicable electrical codes and regulations. In addition to conductor size and component ratings, it is also important to consider the grounding and bonding requirements for the 277-volt circuit. Grounding provides a low impedance path for fault currents, which helps to protect people and equipment from electrical shock. Bonding ensures that all metal parts of the electrical system are electrically connected, which minimizes the risk of voltage differences and potential shock hazards. The NEC specifies detailed grounding and bonding requirements for different types of electrical systems, and it is essential to follow these requirements carefully. This includes using the correct size grounding conductors, properly bonding metal enclosures and equipment, and ensuring that the grounding system is properly connected to the earth. Failure to comply with grounding and bonding requirements can create a dangerous electrical environment and increase the risk of electrical shock or fire. Furthermore, it is important to understand the different types of wiring methods that are permitted for 277-volt circuits. The NEC specifies different wiring methods based on the application, environment, and voltage level. Common wiring methods for 277-volt circuits include conduit, cable tray, and direct burial cable. Each wiring method has its own advantages and disadvantages, and it is important to select the appropriate wiring method for the specific application. Conduit provides excellent protection for conductors and is often used in industrial and commercial settings. Cable tray offers flexibility and ease of installation and is commonly used in large buildings and data centers. Direct burial cable is designed for underground installations and is often used for outdoor lighting and power distribution. When selecting a wiring method, it is important to consider factors such as the environment, mechanical protection, and cost. Also, consider the potential for future modifications or additions to the electrical system. Choosing a flexible wiring method can make it easier to add new circuits or make changes to existing circuits in the future. In summary, when increasing the voltage of an electrical circuit from 120 volts to 277 volts while maintaining the same amperage, it is crucial to upgrade the conductor size to accommodate the increased power demand. A number 12 copper conductor that is suitable for 120 volts and 20 amps is not adequate for 277 volts and 20 amps. A larger conductor, such as a number 8 copper conductor, is necessary to handle the increased power and prevent overheating and potential fire hazards. Additionally, it is important to ensure that all electrical components, including circuit breakers, receptacles, and grounding systems, are rated for the higher voltage and are properly installed and maintained. Consulting a qualified electrician and following the guidelines of the National Electrical Code are essential for ensuring the safety and reliability of the electrical system. Consider also the impact of voltage drop on the circuit. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction, reduce lighting efficiency, and increase energy consumption. The NEC specifies maximum allowable voltage drop for different types of circuits, and it is important to consider voltage drop when selecting conductor sizes. Longer circuits and higher currents will result in greater voltage drop, so it may be necessary to use larger conductors to minimize voltage drop. Voltage drop can be calculated using Ohm's law, which states that voltage equals current times resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. Copper conductors have lower resistance than aluminum conductors, and larger conductors have lower resistance than smaller conductors. To minimize voltage drop, it is important to use the correct conductor size, minimize the length of the circuit, and use copper conductors instead of aluminum conductors. Also, consider using a higher voltage to reduce voltage drop. For a given power level, a higher voltage will result in a low current, which will reduce voltage drop. This is one of the reasons why 277 volt and 480 volt systems are commonly used in commercial and industrial buildings. In addition to conductor size and voltage drop, it is also important to consider the harmonic content of the electrical system. Harmonics are distortions of the sinusoidal waveform of the voltage and current. Harmonics can be caused by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can cause a variety of problems, including overheating of conductors and transformers, malfunction of electronic equipment, and interference with communication systems. To mitigate the effects of harmonics, it is important to use harmonic filters, which are devices that remove or reduce the harmonic content of the electrical system. Harmonic filters can be installed at individual loads or at the service entrance of the building. Also, it is important to use properly sized conductors and transformers to handle the increased current caused by harmonics. The NEC provides guidance on sizing conductors and transformers for harmonic loads. Another important consideration is surge protection. Voltage surges are transient overvoltages that can damage or destroy electronic equipment. Voltage surges can be caused by lightning strikes, switching of electrical equipment, and other disturbances on the power grid. To protect electronic equipment from voltage surges, it is important to install surge protective devices or SPD at the service entrance of the building and at individual loads. SPD are designed to divert surge currents to ground, preventing them from damaging sensitive electronic equipment. The NEC provides guidance on selecting and installing SPD. Remember to consider the load characteristics when selecting conductors and protective devices. Different types of loads have different current and voltage requirements. Resistive loads, such as heaters and incandescent lamps, have a constant resistance and draw a constant current. Inductive loads, such as motors and transformers, have a varying resistance and draw a varying current. Capacitive loads, such as capacitors and electronic ballasts, store energy and can cause voltage surges. The NEC provides guidance on selecting conductors and protective devices for different types of loads. Furthermore, ensure proper labeling and documentation of the electrical system. All conductors, circuit breakers, and other electrical components should be clearly labeled to identify their function and voltage rating. This will help to prevent confusion and ensure that the electrical system is properly maintained. Also, it is important to maintain accurate documentation of the electrical system, including wiring diagrams, panel schedules, and equipment specifications. This documentation will be helpful for troubleshooting problems and making future modifications to the electrical system. It is also important to consider energy efficiency when designing and installing electrical systems. Energy-efficient electrical systems can save money on electricity bills and reduce the environmental impact of the building. To improve energy efficiency, consider using energy-efficient lighting, motors, and appliances. Also, consider using power factor correction to reduce the amount of reactive power in the electrical system. Reactive power does not do any useful work, but it increases the current in the conductors and transformers, which can lead to increased energy losses. Power factor correction can be achieved by installing capacitors in the electrical system. In addition to these technical considerations, it is also important to comply with all applicable electrical codes and regulations. The NEC is a comprehensive set of standards that covers all aspects of electrical installations. The NEC is updated every 3 years, and it is important to stay up to date with the latest requirements. Local electrical codes may also have additional requirements that must be followed. It is the responsibility of the electrician to ensure that the electrical installation complies with all applicable codes and regulations. Finally, remember that electrical work can be dangerous, and it is important to take all necessary safety precautions. Always de-energize the circuit before working on it, and use appropriate personal protective equipment. If you are not comfortable working with electricity, it is best to hire a qualified electrician.